In this video, we introduce the differentiation of hyperbolic functions. These are functions which are constructed by combinations of the exponential function. For instance, we define the hyperbolic sine function. We write it like sine of x, and this is defined by e to the power of x minus e to the power of minus x over 2. So we can also have the hyperbolic cosine, which is given by cos of x, which is e to the power of x plus e to the minus x over 2. Then the hyperbolic tangent is just a tangent of x, which is given in terms of these two, like in trigonometry, sine of x over cos of x, like that. So similarly, we may talk of cosec of x, which is simply 1 over the sine of x. And we also have sec of x, which is 1 over the cos of x, cos of x, which is 1 over the tangent of x, like that. So what we are interested in is finding the derivatives of these functions. But before that, it is of interest to us to look at two identities. The first one is that cos squared of x minus sine squared of x is equal to 1. So if you take this, and the left hand side will give you the cos squared of x, then you are subtracting the sine squared of x. This will be, using the definition, we will write e to the power of x plus e to the power of minus x over 2. And then we square this, we subtract e to the power of x plus e to the power of minus x. We divide this by 2, and then we square that one. So this will give us e to the power of 2x plus 2 plus e to the power of minus 2x. Divide this by 4 minus e to the power of 2x minus 2 plus e to the power of minus 2x over 4, which when we simplify, you can see this will be 0, this will be 0, that will be 4. So we have a 4 over 4, which is 1. Therefore, we have proved that one. As an exercise, we'll say show that the hyperbolic tangent squared of x plus the hyperbolic cosecant secant squared of x is equal to 1. Now let us look at the derivative of hyperbolic functions. derivative of hyperbolic functions. We will start off by saying the derivative of hyperbolic sine of x. How does it look like? This will be the same thing as the derivative of e to the power of x minus e to the power of minus x over 2, like that. This will be e to the power of x plus e to the power of minus x over 2 if we're using chain rule for that one. And what is this? This is the same thing as cosh of x. So in general, what we need to know is that the derivative of the hyperbolic sine of u, hyperbolic sine of u or sine of u, is equal to cosh u du dx. Then the derivative of cosh u can be verified. This is sine u du dx. Then the derivative of tanh of u, this is equal to sec squared of u du dx. Then the derivative of sec u equal to minus sec u tanh u du dx. Then the derivative of cosec u is minus cosec u coth u du dx. Then the derivative of coth u equal to minus cosec squared of u du dx. That's what we have. So as an example, find dy dx if y equal to, let us take the hyperbolic cos squared of x of the ln of 2x, like that. The hyperbolic cosine of the ln of 2x, right? So dy dx will be equal to, we are going to apply chain rule. This will be 2. Then we copy cos, our argument is ln 2x. Then multiply this by the inside function. In other words, we multiply by the derivative of cosh of the ln of 2x, like that. This is going to give us our 2 cosh the ln of 2x. Multiply this by the sine of the ln of 2x, like that. Multiply by the derivative of the ln of 2x, like that. And this will give us 2 cosh of the ln of 2x times sine of the ln of 2x times derivative of ln of 2x. The derivative of 2x is 2 divided by 2x, which will be x. Therefore, we are left with 2 over x cosh of the ln of 2x sine of the ln of 2x, like that. Hello everyone. In this video we would like to introduce you to indeterminate form and L'Hopital's rule. We have this theorem which says that suppose f and g are differentiable on an open interval I that contains C with the possible exception of C itself. If the limit of f of x over g of x as x is approaching C is an indeterminate form of the type 0 over 0 or infinity over infinity, then the limit of f of x over g of x as x approach C is equal to the limit of f prime of x over g prime of x as x approach C, provided the limit on the right hand side exists or is infinite. So basically what we are saying is that if you do direct substitution here and you get 0 over 0, when you replace x with C, you get 0 over 0 when you evaluate the limit, or you get infinity over infinity, then you should understand that, okay, the limit will exist or it may end up being infinite, but how do we evaluate that kind of a limit? The theorem tells us that this limit is the same thing, it's the same as the limit which we will find by first finding the derivative of the numerator and then the derivative of the denominator, then we evaluate the limit. That's what it says. For example, let us evaluate the limit of e to the power of x minus 1 over 2x as x is approaching 0. Then you will observe that if you do direct substitution, you put 0 there, you will get 1. 1 minus 1 is 0. You put 0 here, you get 0. So this is indeterminate form of type 0 over 0. So we get indeterminate form type 0 over 0. Right? So since we have that, then it tells us that the limit does exist. Approach 0, e to the power of x minus 1 over 2x is the same thing as the limit x is approaching 0, because this is our first example. Allow me to write this ddx of e to the power of x minus 1 divided by ddx of 2x, like that. This is going to give us the limit x is approaching 0 of e to the power of x over 2. And then when we substitute 0 there, we get a 1, so we have 1 over 2. Then the second example, we want to evaluate the limit ln of x over x is approaching infinity. So again, you will observe that direct substitution will give you infinity over infinity. So we have type infinity over infinity. And since we have infinity over infinity, we can apply L'Hopital's rule. This will give us the limit x approach infinity. We differentiate the numerator, we get 1 over x. We differentiate the denominator, we get a 1. This is the same thing as evaluating the limit as x is approaching infinity of 1 over x. And now when you substitute infinity here, you get 1 over infinity, which is 0. Number 3, let us evaluate the limit of x cubed over x minus the tangent of x when x is approaching, say, 0. When x is approaching 0, like that. So what do we have? We have the following. If we do direct substitution, you put 0 here, you get 0, you put 0 down there. This is 0 minus 0, which is 0. So this is type 0 over 0. So if it is type 0 over 0, we apply L'Hopital's rule, and this is going to give us the limit. X is approaching 0. We differentiate the numerator, get 3x squared. Differentiate the denominator, get 1 minus sec squared x, like that. And apart from that, when we do the substitution again, this is 0, this is 1 minus 1 is 0, so we get type 0 over 0. So we apply L'Hopital's rule again. This will be the limit. X is approaching 0 of 6x over 1 minus 2 sec x times the derivative of sec x, which is sec x tan x. This is in fact the limit. X is approaching 0, 6x over 1 minus 2 sec squared x tan x. Then when we substitute 0 here, we get 0 on the numerator. There's a mistake, because the derivative of 1 is 0. So this is not there. Right. So we are saying that when we substitute 0, we get 0 over 0, because this will be 0. So this is type 0 over 0 again. So we apply L'Hopital's rule. When we apply L'Hopital's rule, this is what is going to happen. This is what is going to happen. So this will be equal to the limit. X is approaching 0. Then we have 6 over, then we differentiate the denominator, we get minus 4 sec x times the derivative of is times sec x times the derivative of sec x is sec x tan x times tan x, like that, minus the derivative now of tan x, which is sec squared x. So this will be minus 2 sec to the power of 4 of x, like that. This is now the limit. X is approaching 0, 6 over minus 4 sec squared x tan squared x minus 2 sec the power of 4 of x. And then we try to substitute in the numerator. We get 6. Denominator, this will be 0, this will be 1. So we've got minus 2, which is minus 3. Hello again. In this video, we continue to look at the indeterminate form, either infinity minus infinity, and we also have 0 times infinity. So we do not conclude that when we are evaluating the limits, if we get infinity minus infinity, we don't say that is equal to 0. It's meaningless. Similarly, we don't say 0 times infinity, it's infinity. So if we have this kind of indeterminate forms, we manipulate the given expression until we get 0 over 0 or infinity over infinity, because that's when we are allowed to apply L'Hopital's rule. Let us illustrate this through an example where we say evaluate, and we are given the limit of 1 over x minus 1 over e to the exponent of x minus 1 when x is approaching 0, say from the right. And then you note that if we substitute 0 here, we get 1 over 0. Sub 0, it will be 1 minus 1, which is 1 over 0. So this is type infinity minus infinity. Okay, so we simplify. This will be equal to the limit. X is approaching 0 from the right of x into e to the power of x minus 1. When we divide, you get e to the power of x minus 1 minus x, like that. So when we substitute 0 again, this will be 1 minus 1, which is 0. This will be 0. 0 times 0, which is 0 over 0. So this is type 0 over 0. So since we have type 0 over 0, we can apply L'Hopital's rule, and this will give us the limit. X is approaching 0 from the right. Applying L'Hopital's rule, we differentiate this, we get e to the power of x. Derivative of 1 will be 0. Derivative of x will be 1. Divide this, we differentiate our denominator. And when we differentiate our denominator, this is a product. So the derivative of x is 1. So we write e to the power of x minus 1 and put brackets. And then multiply, okay, plus. Then the derivative of e to the power of x minus 1 multiplied by x, which is simply x e to the power of x, like that. And then we check. If we substitute 0 here, we get 1 minus 1. We substitute 0 here, we get 1 minus 1 plus 0 times 1, which is again type 0 over 0. And then we apply L'Hopital's rule again, which is going to give us the limit. X is approaching 0 from the right. Differentiate that, we get e to the power of x. Divide by e to the power of x, which is the derivative of this. The derivative of 1 minus 1 is 0. Then we have a plus sign there. This is a product. We apply product rule on this one. Then we get e to the power of x plus x e to the power of x, like that. Then we can simplify this, get the limit. X is approaching 0 from the right. This e to the power of x over 2 e to the power of x plus x e to the power of x, which is the same thing as the limit. X is approaching 0 from the right. It's up to us now. We can quickly see that if you put 0 here, you get 1. You put 0, you get 1. Put 0, this will be 0. So one may quickly see that this is equal to 1 over 2 for that matter. So that was our example. Then we can look at another example. Let's say evaluate, and then we're looking at the limit of x, the ln of x. X is approaching 0 from the right. Now, if you do direct substitution, this is going to be 0 times, what is the ln of 0? It's infinity. So this is type 0 times infinity, because the ln of 0 is not defined. It's infinity, like that. So we manipulate this, and then we write limit. X is approaching 0 from the right. It's the ln of x divided by 1 over x. Still the same thing, isn't it? So now If you substitute, you will get type infinity over infinity, like that. And then now we can apply L'Hopital's rule to this one. So we have the limit, x is approaching 0 from the right, then this will be 1 over x divided by minus 1 over x squared, like that. And this is the same thing as the limit, x is approaching 0 from the right, so 1 over x times minus x squared over 1, which is the limit x approach 0 from the right of minus x, like that. Then when we substitute 0, we get 0.